Hello! Designing a robot arm sounds simple until you actually try to make one, because suddenly the motors might be too weak, the arm starts wobbling, and the mechanisms that look great in CAD stop making sense. Most robotics videos show the final result, but not the engineering thinking behind it. This video is part of my Pico robot arm series, where I first built the gripper, then started designing the arm itself with the help of AI. In this video, I'd like to share about the reasoning process while designing my robot arm. Not just what I designed, but why I made certain decisions, the trade-off involved, and the problems that I was anticipating even before I print anything. Because CAD is only part of robotics, the real challenge is how to think mechanically. Before opening CAD, I first defined the scope of work, because real engineering often starts with requirement, not the drawing directly. For this robot arm, I want it to be affordable, beginner-friendly, simple to assemble, capable of picking up lightweight objects. For example, I intentionally limited the robot to be 4 degrees of freedom because every extra degree of freedom will also add weight, torque demand, wiring, complexity, and potentially extra failure points. I also defined the workspace to be roughly 20 cm of reach, and 5 mm precision would be good enough for tabletop experiments. Not industrial accuracy, just good enough for a beginner project. So this mindset already eliminates a lot of bad design decisions in the early stage, because constraints are not the limitations, they are the design compass. They guide the design. Once the constraints are clear, I started dividing the robot into two main elements, links and joints. Links provide structure, joints create motion, and most of the difficult mechanical problems happen at the joint level because they need to carry the torque and maintain the alignment. One major design decision in this robot arm was using mostly direct drive joints. That means the servo directly drives the next link without using any complicated transmission system. Now, this is definitely not the most powerful solution, but my goal was to make a robot that is easy to assemble, debug, understand by beginners. At this stage, I also selected the servo choices, not final validated decisions, just a reasonable starting points. For lighter joints, I used SG92R servos, and for the base, I chose to use MG996R because I expect the base to experience higher torque load. Then I moved quickly into a quick sketch before jumping into the CAD because I wanted to answer one question: does the mechanism overall make sense? One of the important things I've learned while designing this robot arm is test the motion early. Before refining details, I added the temperamates and started simulating the motion of the arm. And almost immediately, problems start appearing. The shoulder collided with the base, some servo placements became unrealistic, certain motions look mechanically awkward. This is exactly why early mechanical testing matters. One huge beginner mistake is polishing the CAD before validating the movement. Because if the mechanism itself doesn't work, nothing else matters. So instead of refining geometry, I focused on joint positions, link proportions, and the range of motion. Once the motion looked reasonable, I started refining the joint structures themselves. And one concept that became very important is load paths, meaning how forces travel through mechanism. For example, servo motors are designed to output torque through their shaft, but they are not designed to handle large bending loads. So if the entire arm load sits only on the servo horn, the shaft will experience large side force, which can damage the gears over time. So on several joints, I added support on the other side using standoffs and the screws. In theory, this should help creating a much more stable rotational axis. I also try to avoid over-engineering every mechanical component, but only the necessary parts. For example, the shoulder joint is likely to experience high load, so extra support for the servo horn mount makes sense. A big part of engineering is knowing where complexity is actually necessary. Some joints need reinforcement, others can stay simple. One thing that I have started appreciating during this project is reuse. For the elbow arm, instead of redesigning everything, I reused part of the shoulder arm. Because once a part is mechanically reasonable, reusing it will save us design time, manufacturing effort, and testing effort. This is also where parametric CAD becomes incredibly useful. When I discover collisions or weak areas, I could modify a few dimensions and the entire assembly updated automatically. That flexibility makes iteration much faster, and throughout this project, the entire assembly keeps evolving through adjusting clearance, simplifying geometry, reinforcing weak areas, and improving assembly access. Real engineering never happens in one attempt. It evolves through iteration. Towards the end of the design phase, I started refining the mechanical details. Things beginners, including me sometimes, tend to underestimate, like fillets. Sharp corners create high stress concentration points, which means cracks often started there in 3D printed parts. Fillets help distribute the stress more smoothly across geometry. This kind of small change which makes a big difference. I also started planning cable routing early, because if wires are ignored during the design phase, assembly quickly becomes messy. Cables start rubbing on moving parts, blocking joints, and tangling everywhere. So I added holes and the paths directly into the design. Small details like this are often the things which make our prototype more realistic mechanically. This project taught me about robot arm design is much less about car joint itself and much more about engineering thinking. Because once the robot becomes physical, that's when reality starts exposing the bad decisions. And based on my torque calculations, I already suspect the shoulder joint is undersized. So in the next video, I will print and assemble the first prototype, test this direct drive design, and see if the arm can survive actually the real loads or the whole joint needs a redesign. We are about to find out, because CAD is one thing and the reality is another. See you next time!